Great. Okay, so thanks everyone for coming to the second installment in the series of survey lectures on the physics of learning. Today we're very happy to have Julia Kempe. I think the screen sharing is working if I remember correctly, but Julia will be telling us about synthetic data and scaling laws. So whenever you're ready, Julia, please take it away.
Thank you so much. I will speak about this, and I'll see if my screen sharing magic actually works now. Huh. Let's see. Do you see a big screen like with just synthetic data on it? Yes, Alex, thank you for nodding your head. So I'm going to spend one slide on actually introducing myself, because while we all kind of know each other, it might be making sense to actually speak about what we do in more detail. So my training is in math and physics already a while ago, and I spent more than a decade working in quantum computation, and when it was very hot. And I worked both from a physics and math/computer science perspective in this area. Then I left academia altogether and worked for nearly a decade in finance as a quant. And since 2018, I'm at NYU as a professor of data science and computer science. And in fact, I was directing the Center for Data Science for 5 years until last year. And so my interest in the machine learning, while it, of course, machine learning was present in finance, no doubt, in quantitative finance, so it dates back to that time. But officially, I've been publishing in machine learning only for the last 2-3 years. And of course, I'm mostly interested, otherwise I wouldn't be here, in the theory, understanding, especially the interplay of data and models in my case. And you know, I've dabbled in various sub areas. I've worked a bit in adversarial robustness and adversarial training. And again, interplay with data. Is there a way to make data more robustly learnable? Connection to neural tangent kernel, robustness of Bayesian networks. Recently, we have a paper trying to apply what we spend our years learning to jailbreaking large language models. Another topic, again, around data is in data set distillation. Can we create small synthetic data sets that make models learn well? I worked a bit on out of distribution generalization, again, from the from the theory perspective, analyzing data pruning, or looking what can we say from a Bayesian perspective on this topic. And I've also worked a little bit on implicit bias. But what I want to talk about today is understanding the interplay of synthetic, or I should say synthesized data, model collapse, and scaling laws. So that's for today. I'm going to speak about 3 works. I'm going to speak about 3 works that are based on these. I mean, my talk is based on these 3 papers. One appeared in ICLR, I think this one, the first one, the second, no, ICLM, sorry. One we submitted to NeurIPS, and this one we're now submitting to, I don't know, I lost the track, but whatever the next, ICLR, right. And this is all done, work done with these wonderful collaborators here. So let me just set the stage in a bit informal way. We asked ChatGPT, we actually input a certain text into ChatGPT about synthetic data and synthetic data age, and asked it to comment on this. And what I found interesting is that it gave us this picture that you see on the left. And on this picture, you can see something that I found interesting is that most of the words are a bit garbled. So I thought it was interesting that GPT would output this garbled text, because this is also what the work that we'll analyze will show. All right, so I'm very fortunate that I followed Cengiz in my talk, because he spent a good amount of time on scaling laws, so I don't need to spend much time on it. Just like Cengiz, who has probably also, I believe you showed these models as well. Scaling laws were analyzed both empirically and theoretically, and maybe the most people date them back to the 2020, but there were other works. And what they basically show is how we scale test loss as a function of either dataset size or parameter size of the model. And what people came up with empirically are these scaling laws here on the, by the way, if I move my mouse, do you see my mouse?
Yes.
Yes, okay. So down here, you see that people assume that this training test loss, scales inversely polynomial with the size of the data set and the size of the model. And these are these famous scaling laws, which are used in industry actually to determine the size of a model versus the number of data, right? So these isoflop curves here are quite important. And as we have also seen, they're really everywhere, in video and text and images and math, in language. Everywhere we see these kind of scaling laws. And they're, as I said, useful to derive these isoflop curves, right? Fix what should be the ratio between number of parameters and model size to get the best kind of test loss. And you see these curves, these isoflop curves here that allow this kind of to decide this. So this is also current practice, I presume, in industry, where people don't have the luxury to train a ton of models. It's very expensive, so you better kind of get to the right sweet spot. All right, and one more thing that has been pointed out in the literature, and we can discuss whether it's really something that emerges or if gradually, but people have observed is that various skills, if you wish, only appear at a certain scale, at a certain size of the model or at a certain size of the training set. And whether they appear kind of abruptly or gently is perhaps a question of metric. And also, it's, of course, everything appears abruptly on the log-log scale. So I'm not making any claims on whether this is really a phase transition or not, but definitely certain skills only appear at a certain size. And in fact, what we'll use in our papers is, because François Charton is a co-author, François Charton has worked a lot on a relatively small or moderate transformers, so like up to 100 million parameters on various math tasks. And we use these mathematical tasks as a ground for confirming our theories or studying various phenomena. And here, what we used also in our work is a transformer that learns the greatest common divisor, right? I mean, number A, number B, what's the GCD? Of course, we have algorithms for this. But the interesting thing is a transformer can learn it. And the way the transformer learns is also that, as we train, various GCDs are learned. So first here it learns to predict 3, I believe, and then it learns to predict whatever 2, and so on and so forth. So all these skills also, if you wish, the skills, I mean the GCD that it learns to predict, emerge with training size. And also one more interesting fact, and I believe Cengiz has maybe touched upon this, is that usually in scaling laws, when we analyze them theoretically, we need to make some assumption either on the distribution of the data or on the distribution of the features. And the assumptions we usually make is that the data or the features or whatever are distributed in some inverse polynomial fashion. So this is, you see this from Zipf law in language, but in particular, what's cute about this GCD problem is that the random distribution of GCDs goes with the 1 over I squared. So the probability that you pick 2 is roughly 1/4, which is natural, right? I mean, pick 2 random numbers, the probability that they're both divisible by 2 goes with 1/4, right? So, and so this law actually holds in general. Right, okay, and also for language, we know Zipf's law holds, so also language data is distributed in some sort of, polynomial, inverse polynomial way. And this is one reason, I think, why we get these scaling laws. And if you look, what we did here is we looked at language models. This is still the experimental part of the work. And we looked at how, in Wikipedia text, how is Wikipedia text perplexity distributed, right? And we measured with some big model. So we train a model so that the model's surprise kind of is a measure on this language. And we also see that these kind of perplexities, or if you wish, are distributed in this inverse polynomial way. Okay. So with this in mind, let me show you my favorite scaling law. And Alex, I don't want to insult you. I know you guys have written beautiful papers on scaling laws. The reason I call this my favorite scaling law is because you can prove it literally in one line, right? And you don't need I don't know, Alex, how many pages you had, but I remember it was a lot. So it's my favorite scaling law because
it's more than one line.
It was more than one line. I do remember that opus. It was anyway. So here is a model that this work was done by Hutter. It's the infinite memory model. So what that means is the model has no parameters, it just remembers everything it sees, okay? So that's a very simple model. And the model basically, when it has seen in the training data, when it has seen I and it's labeled J of I, then it will output J of I in the test data. And if it hasn't seen it, it just can't output anything. I mean, random guessing is also fine, but it won't help with a lot of data. And we assume that the data is distributed according to this inverse power law, okay? And now we just want to compute the test error. And the test error, it basically says, on average, when I pick a data point from the test set, I'll be correct whenever I have seen the data point. So I'll be wrong if I haven't seen the data point in my training data. And the training set has size t, right? And so we are wrong if the test point has not been seen. That's the test error. And here is the computation. I just copied this over here. The computation is what's the probability I haven't seen it. So it's a probability that p appears, the point with which the point appears. And then it's 1 minus p of I to the power t, which means like for all of the t data points, I haven't seen this point. And this is the one line. Even this line, by the way, requires 3 dots because somewhere there is a bit of a gamma function in there. But nonetheless, when you just compute this infinite sum here, you just get that you scale with t to the minus c. T is the size of the data set. And c is a function of the beta that comes from the data distribution here, right? So if it's distributed with an exponent minus beta, then the scaling law here, test error scales. So I think this is beautiful because it gives the essence of all scaling law proofs. I mean, you might disagree, but in some sense it does. And here you see how test error, right, scales basically. All right. And now what happens is, here's where our work starts. What happens if data is not anymore natural data? What happens if data is, I don't want to say contaminated, or maybe we say enriched by outputs of models? So we know, I mean, since 2021, it's become fashionable to output, to ask DALI at the time, maybe you recall Stable Diffusion, and now language models, and these models produce a lot of output. And this output goes back into the training corpus. Let's not kid anybody. There is lots of GPT-generated text. I mean, now it's estimated already 1% of all internet text is generated by GPT. I don't know how this is measured, but it certainly doesn't strike me as totally false. And, all these images appearing on the web, there's this very standard benchmark called Lion. And it can be shown that Lion already contains generated data from diffusion models. So we are in a situation where the output of our models becomes the input of our next generation of models, right? So that's certainly true. And the question we ask is, we ask what happens to the scaling laws. But before we ask this question, let me say that in what follows, we will paint a bit of a doomsday picture and see that generated data is actually not so good for scaling laws or for training or for anything, but there are clear benefits of generated data. There's no question. And there's lots of literature going back to 2021 or even more that has various cases where they use a model, it generates data, and then they train another model or fine tune or whatever, and it becomes better. And no doubt, these works exist and they're all correct in their setting. But when you look at them more closely, what is usually the case is that they use a model to generate data, and they use it for different downstream tasks, which usually is on a weaker model. So for instance, we use Stable Diffusion or ChatGPT to generate lots of text, and then we fine tune some small, whatever model with this text, and lo and behold, it becomes better. This is often the case. And so also there's critical work that really shows if we had the data of that big model that we use to generate data, if we just had that model's training data, we would do even better. Okay, so models are used as a proxy for a lot of training data that we don't have, and then they have a certain benefit. And then, so there is this paper which actually only appeared in Nature now, but it's been around for over a year. It's, I think, May 2023 that this paper appeared, and it appeared in Nature, I guess, in June or July here, which speaks about this model collapse. And what these people analyze, to some extent, is they say, okay, here's our data, and we train a model on it, internet data, and it's all good. But then the next data has some real data and mostly fake data. fake data, meaning generated by the previous model. And now we train another model on it and another model on the output of the previous model and what happens. Okay. And so what they show us on very simple examples that model collapse happens. So for instance, they train a small diffusion model on MNIST, and then by generation 20, it's, you know, it's all one gibberish, weird 0-9 number. And there's more of these things. And the argument here that they make is, when you have a Gaussian, you can think of it really with simple Gaussians. And when you, this is some sort of latent space of some diffusion model, but just think of sampling a Gaussian with a finite number of samples and then training the next model on it. So what you will do is you'll miss out on some of the tails, and the next generation will be more peaked. And the next generation will be even more peaked. And this way you'll kind of get this kind of model collapse, right? So it's a finite sampling effect. Basically, so these works were out when we looked at this, and there was also these two works that used iterated image generation. And you can again see this is the original data, and after you retrain it, after, you know, on fully synthetic data, you get this kind of very not nice looking face, right? Or here, this kind of weird texture of the beard. So, I mean, people have really analyzed this in various settings to show that things like kind of look weird. And so what we asked in our first paper, because we liked scaling laws, is how will the scaling laws change when we start having synthetic data in our training corpus, okay? Will we still improve, or will we degenerate up to total model collapse? So this was the starting point of our work. And what we show is, and okay, why is this, why do I like this work? I mean, first, it maybe makes kind of a relevant statement. But what is really nice is that this gives rise to a lot of new things to analyze. I mean, the amount of math you can do in this model collapse setting is just staggering. And, you know, we are writing the 5th paper on it now, and there are other people, lots of more. I mean, it's a whole explosion, and up to really nice theory that you can do in this setting, and really nice tools. I'll mention them later. But let me. This was the first paper, so let me tell you what we show in this paper. So the first is that we ask, how is synthetic data different from normal data? And in various settings, we show that what it does is, if normal data has this kind of tailed distribution, the zip law, remember, what we can show is that synthetic data will generally cut off the tails. Okay, so when you synthesize data and you have a finite sample of, you know, in your training data, then you will get very cut off synthesized data. And then when you train the next model on this kind of half cut off data, your scaling laws that are supposed to go down on a long log scale will start to taper off, and they will taper off even more. And what we then show, and I'll give you more detail, is that essentially the scaling stops, and then you can give it as much infinite synthetic data and it will just not scale anymore. So that's nice, and there is a bit of nice math in there too. And there are various nice effects that happen when you start mixing real and synthetic data, and so on. So I'll get into this. And the experiments we did was actually we forced ourselves and actually trained Llama 7, fine-tuned the Llama model on it. But we also used this beautiful math transformer for math work to make initial statements, because it's much cleaner setting. All right. So what we can show is that what generally happens when you have a finite sample training is you cut off the tails. And most language models, when they do inference, so when they synthesize data, they cut their tails even more, because usually there's something called top P inference. Usually when you output the next token, you cut off your distribution to have a cumulative weight of only 95 or 90%. So you deliberately ignore the tails in the data. And when you generate this, you will see that you get both tail narrowing and tail cutting. Because if you look at this token by token, then you look at perplexity, it narrows the distribution. So that's a first observation, is this kind of synthesizing of data does something to the tails. It both narrows them and cuts them. And also sampling bias ends up cutting the tail, right? So that's observation number one. And then we observed this. So what we did is we trained this Llama model on Wikipedia. We fine-tuned, I should say. Then we had it output, again, continuation on the Wikipedia data, and we retrained it, and we measured what happens to the distribution. We see the original data with this beautiful tail, and then how it becomes narrower and narrower, just literally. I mean, just as our theory predicts, this is what happens when you generate data from models that are trained on its own output and so on. And for GCDs, for this transformer, what happens is that here's the GCD distribution, and when you use only finite data, it will predict up to basically here, and everything else is cut off as well. So this really happens, this cutting off of tail. And then what we show for this Hutter model, the one that I mentioned, the favorite model with the one-line proof, and then we generalize this to more sophisticated models, is instead of having a scaling law that scales with, remember, t to the minus c, and c was this beta minus 1 over beta. So instead of just having this term, you get an additional term where k is the point where the tail has been cut in the synthetic data, right? So you get an extra term in the scaling law, which is very not nice, because here is the original scaling law. Remember how we scale with the sample size? Here's the test error. We're supposed to go down on a log scale. And what happens is when we, when we have generated data without tail, well, we stop, right? And we stop learning. So we first scale nicely, and then that's it. More and more data doesn't help. And we see this both for the sample. This is the sample size of the training data, and this is the cut of k. In any case, you get that the scaling laws are just dead. So that's it. And you can, there's various scenarios you can prove this again and again in various different scenarios. And then, of course, we ran, the thing is with the theory, you think this is the sophisticated piece. But let me tell you, running this llama experiment, just getting these 2 lions is like 3 weeks down the drain. So, but we did run llama. So as I will describe it in a second, and we see the original scaling law. And then here we see the scaling law once it's trained on this AI generated data. So whatever our theory predicted is actually really happening here in this llama model. And I'll describe the example in a second. Right. And then for the GCD, for this greatest common divisor, what we did is we trained a transformer on some finite data set. We trained it, and then we had it generate data, and we see once we train it on this AI generated data, it stops learning, right? And here's the skills. Remember, I showed you these various skills that the thing learned, and here's the one trained on AI data, and it stops learning its skills. So not good news, basically, and confirming the theory. And then we studied what happens if you do this multiple times, what happens with these scaling laws. And what we see is that we basically, instead of scaling with 1 or with t to the minus c, this was in the Hutter model or many other models, this is a very universal law that we see, we would scale with n times t to the minus c, where n is the number of iterations of this model learning on itself, right? So when you have this loop of stuff. And, we also see it on more realistic models that are not just infinite memory. Here is a kind of bigram model where we make the infinite memory model probabilistic, and we see this decay with n. And we, and here are just to give you an idea of the experiments we had to do. So here is this Wikipedia data, which we split into chunks of 128 tokens, so words. And we have 2.2 million such chunks. And for each chunk, we split it into 96 tokens that are just input, and then the 32 next tokens that the thing is supposed to predict. So we train it on the data, and then once it's done, we ask it to generate its responses to these tokens of length 96. And we use this as our new training corpus. And again, fine tune the model. So these are the experiments we did to show that these theoretical predictions actually hold. And as you see, here is the training curve for 1 generation. So this is supposed to be more of a line, but you get what you get for this llama. And here is the test perplexity, right? And here is these various curves where things go off the rocker, basically. All right. Just to say that we proved it for various generalizations of this infinite memory model, where we made it probabilistic and we made it autoregressive. And each time it becomes basically the business of summing infinite sums that become more and more complicated. But one can do it. And then you can mix these various effects. You can have this top P inference that I mentioned, and finite data effects and multiple generations. In any case, the message is always clear that the scaling laws will taper off in all these models. And as I said, also in real life. Now we ask what happens if you mix original data and AI data, because this seems to be the more likely scenario. It's not going to be suddenly everything GPT generated. What if you have like a proportion pi of real data and a proportion of 1 minus pi of AI data? And what we see is, and that's what's really cute, we thought, that the scaling laws, and this you just have to compute, right? The scaling laws doesn't do something really funky. They first go down as they should, then they taper off as we know they do if we have infinite synthetic data. But if you have this mix, then after a while they pick back up and they start training again. And this is for this Hutter model, for the infinite memory model. For models where we have slightly different assumptions, we get more like an S-curve. Instead of this like plateau, we get a bit of a stopping and then restarting again. So I don't know, actually I haven't thought about it. I'm sure there are effects in physics that have similar, similar kind of behavior. We haven't made this connection, but the sums that we had to sum, etc., they definitely appear also in physics, I'm sure. In any case, so we get that. And we also got this for our Llama another 3 weeks later. We also got this for our Llama model, where we see that here's the training curve on the original data, here's some mix, first generation, second generation, we see this kind of weird behavior also happening. All right. And we also can, with all the formalism in place, we can analyze when does AI data benefit. And remember, I mentioned this, the strong models help the weak models. So you can analyze this and you can see that when real data is really scarce, so when there's so little real data that it's below the kind of tail cutting of the AI model, right? In that case, it actually helps the AI data for a while. Okay, so we can even analyze this effect of AI data as beneficial in some regime, as I mentioned. Right, so let me jump over it. What we did, which was much, as I said, theoretically much more sophisticated, is we fully analyzed kernel-rich regression, we fully analyzed kernel-rich regression on this model collapse phenomenon with synthetic data. So we assumed some Gaussian data in high dimensions with some label noise and some ground truth vector that determines its regression, right? It determines the label. And then we did like a whole random matrix theory analysis of this thing. So here is the graph, right? So you have this data, and I can only draw a classification, not regression, but think of regression here. And you have a bit of label noise, right? And you fit a model, and then the model is fit, but it's not fully right because there's this label noise and there's finite sample. And then you regenerate the ground truth with this model and you train another model. And eventually, when you do this, you get more and more misclassified points, right? Here's the schematic. And what we get is, again, this n times, so we get the normal test error, which scales like with the data set size. And then we again get this n times scaling. I call it scaling because it really depends on the regime. You can do a whole phenomenology of this model collapse. But we again get this n times term that kind of starts dominating when you repeat this process a bit too much. And recent work, we now analyze this setting with mixed data, and we get all, there's a very rich phenomenology of what effects there are and when does it help and when over-parameterized helps and when under-parameterized helps. And you can make all kinds of prediction about bigger models, smaller models, all that stuff. All right, so the kernel-rich, it gives us a very interesting analysis because it also shows us how optimal, there's usually an optimal regularizer. For kernel-rich regression, you can show when you should regularize to kind of have the best test error. And we see also that everything gets screwed up. And in particular, the optimal regularizer also moves away. So generation 0, you kind of have the optimal regularization also changes as a function of these, synthetic data, basically. Right, so lambda changes. And right, I think that's all I wanted to say about this. And we did this for all kinds of covariance matrices. There's a really rich picture. You don't just do it for isotropic Gaussians. You can have some sort of power law on the covariance and analyze what happens. And I think Hugo, I saw Hugo in the audience. So they did an analysis in the clean case when all the data is natural data. And we can extend all this analysis to the synthesized data setting and the iterative setting, basically. All right. So where does this leave us? It actually is not so great, because what it means is if you just have more and more synthetic data, the scaling laws will disappear. So it won't help to have more data. It's kind of not great. These skills that are learned will be unlearned. And these kind of weird mixing effects can happen where you suddenly plateau, and if you don't know that you would be plateauing, you would stop when you should actually continue training. But there's also interesting new kind of phenomena and so on. So with this in mind, we asked, is there anything we can do about this? And this is this latest paper. It's called Beyond Model Collapse. Scaling up with synthesized data requires, okay, the referees butchered us on the word reinforcement, so we will change it to verification, I should say. In any case, here's the experiment that we did. And this time we did it on another math problem, namely computing eigenvalues of 5x5 matrices. Just to illustrate, so the point here is that if you have a verifier in the loop that decides which synthetic data is good and which one is not so good, and then you throw out the bad one, in that case, you can actually avoid this model collapse. That's the message. And you can analyze all kinds of verifiers in this setting. So here's what we did. We took these 200,000 data points and we train a transformer to predict the eigenvalues, these 5 eigenvalues, to an accuracy within 2% in the relative L1 norm. So not exactly, but nearly good accuracy, a good approximation of the eigenvalues. And if we do this, about 2/3 of the test prediction are pretty good eigenvalue calculations. All right. And then we take this model, right, and we generate more matrices, and we ask it to compute the eigenvalues, and we use this as new data points. So it's not the real eigenvalues, but these predicted eigenvalues, right? And then what we do is that we have some sort. So if we do this just like this, then the model will just start on, won't learn anything after a while. But if we have a verifier that basically throws away 80% of the data, namely the data that really isn't so good. I mean, the verifier in this sense, it defies the purpose because the verifier needs to know what the real eigenvalues are or not in order to do the pruning. But we later show also that you can have a not fully perfect verifier, but just some verifier. In any case, when the verifier prunes the data, then we can actually get really high accuracy, and we can go beyond the accuracy of the original model. Okay, so verification not only avoids this model collapse here, but actually allows to bootstrap. Now, if you look at this, this is a cute math experiment, but of course, if you think about it for a moment, you'll say, well, yeah, if you know the ground truth and you kind of prune the data to just keep the ground truth, well, obviously you get better. And that's of course true. But the point here is that this allows us to analyze various intermediate settings. And for instance, one interesting thing is you could ask the model itself, you can ask the model for each kind of matrix to generate several answers, several candidate solutions, and then you can ask the model, which one do you want to keep? And the model will just be completely confident and completely wrong in keeping stuff that's not good for it. But if you use some verifier that is not the model, but who has some notion of ground truth to prune this, then you again can improve. And you can study this in all these settings where you have a verifier, you have ground truth, and you have a model, and they can be on 3 different axes, so to speak, if you want to think of it in the linear regression setting. But generally there are thresholds after which a verifier can restore kind of the performance. And what this means is that basically what is needed is not so much somebody who generates data, but only somebody who can rank and verify data, right? So a verifier is enough to avoid model collapse, but you don't need so translating it to human, you don't need a human to write a new Shakespeare to train the new model. You just need a human to tell us whether this is better text or worse text, and throw away the worst text and keep only the better text. So having a verifier who ranks is enough to avoid model collapse, basically. And so this is one work, and we have several more on this theme coming out. I don't know how much, let's see, what am I doing in terms of time. So this is this beam search experiment that, let me explain it again. So here we have this model that we trained to 66% accuracy, and we ask it now to output 50 different candidate solutions, right? And when we ask the verifier to actually, kick out all the bad ones and keep the good one, it will never, it will just keep this accuracy. It won't get better. But if we ask a real human or some slightly imperfect verifier that's not the model itself, then we can bootstrap ourselves and get better accuracy out of synthesized data. This is what this experiment shows here. I want to say this is really a topic. I mean, this is a topic that is of wide public interest. I mean, we had the New York Times come and write about this. We have the Atlantic that was, I don't know, they wrote about it. There's lots of the work about it, and it's very interesting mathematically, I find, this kind of, because you have all kinds of tools. Let me just summarize here and tell you about the tools we use. So as I said, the bad news was that scaling disappears, skills are unlearned, and so on. But when you look at what you can do, scaling is not all you need, obviously. You need to either effectively watermark your data so that you can throw out the synthetic data, or you need basically human verifiers or verifiers aware of the ground truths to prune the data, basically. What we liked about it is that mathematically, this was really interesting. We could use random matrix theory. There is my collaborator, Elvis. He really was happy when he could apply operator valued free probability theory, because when you get to clean and synthesized data, you will have, if you have a covariance matrices, you will have two different non-commuting matrices, basically, and you need to kind of say something about the eigenvalues of these things, and that's not always so easy, but I guess it's possible. And you get these feedback loops. So there's some works, not ours, that uses some sort of notions of control theory to make statements on how much real data do you need compared to synthesized, so that you get a stable loop and not a loop that degrades. And so it's quite cute. And that's, I think, that's all I had to say about about this work. Thanks.
Great, thanks Julia for the very interesting talk. We have plenty of time for questions. I think you almost perfectly hit the 40-minute talk, 20-minute question breakdown. So we can open the floor to questions now. I think I see, I don't know if Hugo was first, but maybe we can go to him.
No, I don't have a question. I was just uploading.
Oh, okay. Good. Okay, I see a few more. Maybe Alex?
Oh, thanks. That was a great talk. I had two questions. So it seems like the key part is trying to find a verifier that's cheap relative to generating original data. So if you have any thoughts about what problems are suitable for that and which ones aren't, that would be great. And maybe the other thing is that you flashed at the end something about free probability. I didn't know quite. Maybe I missed something, but yeah, if you can elaborate on what role free probability is playing, that would be
so this
super interesting.
This one I will actually defer, because we are in the middle of writing this, and you know, I'm looking through all these proofs of Elvis, but it's basically, yeah. Let me defer that question to, and you know, once we have the paper out, and then I'll get back to you with happily. But on the what do we? So the first question was, what do we really? Which problems are amenable to having just a verifier? So in fact, I would say everything, but in particular, the common practice now is to use RLHF when you train large language models. In the end, you have this phase where you do reinforcement learning with human feedback. And what it does is essentially the model starts generating, and you have a human rank the outputs, okay? And then you train a reinforcement, like a policy model, to generate more such data, and then you fine-tune the model on this. So in other words, you're using a human here, not to generate more data, not to annotate, but literally just to rank. The human gets presented with 2 outputs, and it's very boring, and they have to say, this is better than this, or 3 outputs, or 5 outputs, right? And this tends to really boost the performance of language models. And what we show here is that this might be enough, literally, just to rank, as opposed to produce your own text, might be enough, once you have trained on enough text that has been produced, obviously, to at least not lose performance.
Thank you.
Good. Maybe Bison next?
Yeah, thanks for the great talk. I was just curious about this comment that you made about the AI data does help when the data is scarce. Can you just elaborate on that? Or like, do you have a quantitative measure of what you mean by scarce?
So the one thing we showed is that you have an AI model trained on lots of data. And now you have it generate, and we know this amounts to cutting the tail of the distribution somewhere, okay? Yeah. And now let's assume for your real model, because the AI model comes from OpenAI and they have lots of money, they can train the model, obviously. Now you don't have that resource, you want to train the model on your data, whatever. But you have very few data. And so what has been observed is that it helps to inject into the training set, data from the OpenAI model, because they have such a wealth that they are, even when they with their tails cut, they are better than what you have in your training set. So this is often how under the hood these kind of things work when their claims are made that AI data helps. Or in some, I mean, this is the simplest case, and then more sophisticated is that often nowadays you ask when you have some data, language data, and you ask GPT, can you rewrite it to me 5 different, and you augment the data this way, and then you again use it for train your model, and again it helps, which is in disguise in some sense a little bit the same effect, right? That you have a very rich model trained on a lot of data, which will help you augment your own data. Do you see what I'm saying? And then for images.
I guess you had these toy model settings like kernel regression or something. And in those settings, do you see this phenomenon of when the data is scarce? Then
yes, what I showed there, these kind of, I was a bit fast on these curves. That was on these variants of the Hatter model, this infinite memory model and its variants, up to kind of finite memory variants. In these variants, we could show that if you have one model trained on a lot of data that goes, we always assume some sort of power law on the data. So when we assume the model has been trained on a huge corpus T, and then we train a little model, and we add this data from the big corpus, then for a while the little model will improve. This is kind of the scenario that we show. Show like mathematically show, right, with the proof.
Okay, thanks.
Good. Maybe Bernd next.
Okay, so thanks for the interesting talk. I have a question regarding the concept of verifiers. So could you use a model trained with a different initialization as a verifier, or use an ensemble of models as a verifier, which were trained on the same data?
Yeah, this is a very good question. So it doesn't seem to be the case. I mean, again, it's very hard to get 2 Llama models trained on the same data with different initialization, right? So in the big, I don't know what will be in the big setting, but as far as we can see that having this done twice and then having one verify the other might not help if they've been trained on the same training data. But again, this is, I'm saying this very tentatively because we haven't really analyzed exactly this setting.
Thanks.
I mean, I should say in linear regression, what I'm saying is probably true, just thinking through the proof now. Yeah, I think. But again, if it's the same training data, it won't help you much. But again, I can't make statements on bigger system. But for instance, we had experiments where we have Llama 3, and then it outputs gibberish, and we have Llama 2, so a weaker model, verify, and that already gave a bit of a boost, and we have some explanation for it. So it really depends, right?
Thank you.
Very good. Looks like Bryce also has a question.
Yeah, hi, Julia. Thank you for a nice talk. My question is very similar to that of Maysam, and I think you have answered half of it already. So when you use synthetic data and you get a boost from training with real data when the training data is small, it feels very similar to augmented data, right?
Yes, so this is, you're making a very good point. Sorry, but I should let you ask your question. But
no, so I wanted to know if, so I don't know how easy it is with the language, but with images, it's very easy to generate augmented data by adding translations, rotations, scalings, etc. I wanted to know whether it's possible to test, to what extent it is the equivalent of augmented data or not.
Right. So again, this is actually, it's a very good question. So there is no again, no doubt that augmentation helps, and we can think maybe of the augmentation as like synthesized data, although this is not quite the case because it depends, right? But it's already it's a different model. If you wish, augmenting data is not synthesizing data with the same model that you're training. It's kind of a different. So we get into this realm of what if a different model helps another model, right? And again, I would claim it helps to a certain extent, and eventually it stops helping. I think that's ultimately true.
I see. Thank you. And you showed us a figure when you have a mix, you see the error going down, then there's a plateau, and then it goes down again, and you recover the usual scaling. So there's a characteristic scale there. Do you know what drives that scale?
It's beautiful that you asked this question. It scales exactly inverse proportional with the fraction of synthesized data.
I see. Okay,
it goes with 1 over pi. Yeah. Oh, you were expecting this because I keep being asked, oh, do you have an intuition for this? And I actually don't really, but I haven't thought of it enough. But it exactly scales with 1 over the fraction of synthetic data. And in the limit of pi goes to 0, so excuse me, 1 over the fraction of real data, I should say. So when this pi goes to 0, then you just get an infinite plateau that goes straight. Yeah.
Okay, thank you.
Yeah, I see one more question from Darshil, I think.
Hi, thank you for the wonderful talk. I had 2 questions about the first half of your talk, basically scaling laws. The first one is that in most of your analysis, you use the change in the Zipf law or distribution of, let's say, tokens to see the effect on scaling law. But in principle, there can be higher order changes, right? Like, let's say the distribution of tokens is the same, but the correlation structure has changed. So is there some quantitative way that you can analyze this?
This is a good question. We have not analyzed this because we already suffered with just, first order, so to speak, analysis. I don't know. So yeah, no, I don't think anybody analyzed, and I see Mathieu here, so that's a Mathieu question, right? So I don't think anybody has yet analyzed what happens to the correlations that are longer range, right? When you start synthesizing data. And I would suspect that probably, that the more top hierarchy would die out first, but it's an excellent question. I don't know. It's a really good question.
Okay.
Wait,
and the second question is, yeah, sorry.
Yeah, no, I was wondering what your second was.
Okay, yes. So the second question is more for clarification. Maybe I missed this part. So you said that there's 2 ways that this distribution changes. One is it gets narrower, and the second is it gets cut off. So for Llama experiments, which one did you see that was more prominent?
I think it's the narrowing, and the reason is when you just do a simulation. We're too lazy to compute it. You can compute it too, but we just did a simulation. What happens if token by token you have this 95 probability? So you cut off the 5% of mass, right? And you do it token by token, and then you look at all these texts that let's assume you do this token by token, you generate text of 100 tokens, and then you analyze the perplexity distribution of all these. Cutting the tail token by token translates to a narrow tail in perplexity space. I think because you get some sort of combinatorial factor that then changes and makes this narrower, basically. So both happen in Llama.
Okay, thanks.
Good. Okay, Hugo, I think, as well.
Yeah. Thanks so much for the talk. I really loved it. I just have a very quick question just to clarify for the plot where you showed that there was like a decay, plateau, and then the decay. Was it for Hutter or for the kernel ridge regression
This
model?
was for Hutter. This is for Hutter. Okay. And the very sharp plateau is literally only true in this infinite memory setting, and then it becomes the smoothed out setting. And we have different results now for the mixing stuff in the kernel ridge regression. For mixing real and synthetic, things look a little bit different again.
Okay.
Yeah.
Is this paper out, or is the one that you're
the mixing one is we're rushing to write it in the next whatever.
Okay, got it.
I think I'm happy to send you a draft once it's in a state that can be shared.
Nice. And I just have a very quick follow-up question. for the, maybe it's like anticipating a bit, but if you, for this plot, you were like fixing the total number of data, right? And then if you want to augment the data using synthetic, you have to sacrifice kind of real data. But if you kind of fix the number of original clean data that you have, and that you allow yourself to add as many synthetic examples as you want, I guess there's a trade-off somewhere, right? Because if you don't add any...
I should have spent a little more time. We have this setting, and we had this graph where, under the benefits of AI data, I showed a graph where things kind of first improve and then stop improving. So that was indeed the case. Whereas
I'm sorry, I missed it.
No. Okay. I should have just, this was actually my bad. So yeah, so we have these graphs, and first it helps and then it stops helping, basically.
Oh, yes. Okay, thank you.
Good. I think I saw Eva's hand next.
Yeah, thanks for a wonderful talk. I'm kind of groping for a question about whether your methods or your results apply to the kind of methods people are using to bootstrap for reasoning, where I gather they kind of generate chain of thought. There's something called STAR, for example, that seems to be used for that. Do your results apply to that sort of thing as well?
So you're asking, let's see, when you say, so I don't know STAR, I'm sorry, but a chain of thought is when you ask the model, now go step, is this kind of thing, go step by step, give me an answer, and then I have an interactive communication? Is that what you're referring to? Or do you refer to having two models check each other? I don't know which of these two is your question is about.
Well, it sounds a lot like your verifier, but it's about generating kind of reasoning steps. But it seems sort of on the same theme of it being sort of self-supervised, the model generating these these rationales, and then keeping the ones that are better than the among the set that's generated, keeping the ones that are better. So yeah, it sounded.
So, I mean, we didn't try. I mean, we didn't try this because even analyzing it for regression was a nightmare. If I may be honest, I think whatever we did kind of applies to when you have some other thing verifying. So generating stuff and then throwing away as a function of what other models say or humans and so on. And so in that sense, there might be some weak applicability, but I haven't thought about this yet, and I'm not sure how much we can say about it, frankly.
Okay, thank you. I'll share the thing I have in mind in the chat in case it clarifies.
Thanks.
Yeah, thanks again for the talk.
Great. Okay, I also see a hand from Noam, looks like.
I'm not in an optimal position to ask, but I'll try anyway. Very good talk, but I was just curious about two things. One is there any effect of doing some kind of curriculum? So if you first train with some fraction of the original data, then combine some fraction of the synthetic in this whole story, that can affect the scaling laws.
I think in, let's say, the Hatter model, I don't think it really matters in what order the data is presented. So for these proofs, if you just use the same data and just reorder it in whatever way you like, it's not going to help us because you're missing the tails. I mean, the statement is always about missing out on a certain, low frequency, low probability regime, and nothing will help there. What happens in reality, I don't know, hasn't been tried. I mean, I haven't seen experiments where people said, let's first present it with the real data and then the AI data, and let's see what happens. I suspect it won't change much, frankly, because it's missing. It's basically, it's missing something.
Yeah, it's missing by some fraction, right? So if you show the real data does contain those tables, but you're only showing it a very small amount of that distribution, you're saying that it will get cut because of that. But if you were to somehow, in a clever way, sample this, it might change the story a little bit.
I see. Oh,
I understand that in your models,
it
won't work because you have something that doesn't depend on order. But
yes.
in real world, I assume it's not like that.
We have actually a section in that paper that we say called buying tail. And what we basically analyze is what if for the real data, we consciously decide only to get tail data, right? We have a budget, we have so many, we pay $1 per data point. What happens if we buy tail? And there, indeed, you're right. I mean, if we, for the real data, try to get as much tail as we can, there is an improvement. But again, it requires this kind of sort of verification in the sense that you need to know what data you need.
Okay, thank you.
Okay, I think I saw a few hands that went up and then went down. So just to check that, was everyone else's questions addressed, or are there any more before we wrap up? No, looks like nothing. Okay. Well, then we should all thank Julia again for the very nice talk and for the nice discussion afterwards. The clapping emoji, and let me